This is a recording for lesson 4 that happened on either February 4th or February 5th. Again, today we're working on some of those nuances as we put lesson 1 through 3 together for the practice. We're adding just a few new pieces that kind of help us get better at using those horizontal asymptote rules. We started today's lesson by looking at me giving you some facts and then you writing out those facts into a function. So as I put these together, and this was an opportunity for us to think independently in class, we're writing out a function so we know it has to be equal. I know that this is crossing at -4, 0 for my x-intercept. So that is written as a factor of x plus 4. Because it is crossing, that tells me it has a multiplicity of 1. The second fact has an x-intercept that bounces at 0, 0. Again, when it bounces, that tells me it has a multiplicity of 2. And x-intercepts belong in the numerator, so I know that numerator has an x squared factor. We can also write that as x plus 0 squared, or x minus 0 squared. They mean the same thing. I prefer just x squared. Next, I read for my next fact that I have a vertical asymptote at x equals -2 with a sign change. As soon as I read that I have an asymptote, that confirms that I have a fraction or a rational function. And I know that my vertical asymptotes go in the denominator. So that's going to be a factor of -2. Sign change means multiplicity of 1. The second fact for my vertical asymptotes is that I have a vertical asymptote at -1 with no sign change. Again, vertical asymptotes go in the denominator. If the answer is -1, the factor is +1. No sign change means multiplicity of 2. If my horizontal asymptote, which is my next fact, is moved away from the origin, that becomes my a value. So I have a -3 at the beginning. Now that works with rule 2, which says that the numerator degree is equal to the denominator degree. So I would want to check over my function and make sure that the degree of the numerator is equal to the degree of the denominator. Based on this, I see I have a third degree function in my numerator because there's 3 factors, and a third degree function in my denominator because of those 3 factors. So rule 2 is in play, and again, that a value becomes -3. Now, I expect you guys to be able to make that complete list based on looking at a graph or looking at a list of characteristics. If I look at this graph, I first notice that I have an x-intercept at 0, 0 with a bounce. That implies in my function that that factor has to have a multiplicity of 2. I have an x-intercept at 4, 0. That is crossing. So it has a multiplicity of 1. If I look at, or put those in my numerator, I'm going to have that bounce factor at 0 and that cross factor of -4. Next, I notice that I have vertical asymptotes. That confirms that I'm going to have a fraction. If I look at the right asymptote, it's at x equals 2. Now looking at the end behavior, one end is going positive, one end is going negative. That's a sign change because one is going to positive infinity, the other is going to negative infinity, meaning that I have multiplicity of 1. Again, from the x-intercept to the factor, we want to adjust the sign. I also notice that I have a vertical asymptote when x equals -1. Looking at the behavior near that asymptote, both ends are approaching positive infinity, so they're both going in the same direction, which means no sign change, which implies multiplicity of 2 in my function. Then I locate the location of that horizontal asymptote, which appears to be at y equals 3, and that 3 goes in the beginning of my function. Again, I had to make sure that the characteristics were correct and in the right spot of my function. In order for rule 2 to show up, the degree of the numerator needs to be the same as the degree of the denominator. I've confirmed that by looking at the multiplicity. This is definitely something you want to check because it's easy sometimes to forget adding in that multiplicity. If our horizontal asymptote is at y equals 0, that is rule 1 in those 3 horizontal rules, and it tells us that the degree of the numerator is less than the degree of the denominator. When we have our horizontal asymptote, and again, this is observed, then I have to solve for the a. That is something that has to be calculated or solved for. We cannot interpret that from looking at the graph. So as I look at my function, again, I want to slowly build my function by looking at the x-intercepts and the behavior. Those go in the numerator of my function. So I locate my x-intercept at 0, 0, and that is bouncing, which again tells me I have multiplicity of 2. The other observable features are my vertical asymptotes. So if I look at the asymptote on the right, it's at x equals 3. Again, those ends are going opposite, so that's a sign change, which corresponds to a multiplicity of 1. I also notice that I have an vertical asymptote on the left at x equals -3. That one has no sign change, which means multiplicity of 2 in my function. Now for this situation problem, again, I cannot observe the stretch or compression, that a value. It is something I need to calculate. So I'm going to grab that point that was provided for me, plug that in for x and y, and solve for a. So into my y value is going to be -3.125. And again, this is going to help me solve for a. And then I'm putting in -5 for x. I want to do some of the simplification before I pick up my calculator. Anything squared is always positive, so -5 squared is +25. -5 minus 3 more is -8. -5 plus 3 is -2. Squared is 4. Anytime I have a fraction, I'm always going to cross multiply. -3.125 times -32 is 100. Solve for a by dividing by 25, and a equals 4. Again, we were not able to observe that from the graph. We had to do the calculations. So my last step is I want to replace that a with the number 4, because that's what we just calculated it to be. If your asymptote is at y equals 0, again, that is the only time you have to solve for the a value. Let's try a second one. Again, make sure you're copying down these graphs in your notebook. If you're watching the video, you should pause, write down as much as you know, then come back to the video and add in or make corrections. The first thing I notice is that I have an x-intercept 2, 0 with a bounce. Again, that implies multiplicity of 2. I have an x-intercept when x equals 4 with a sign change, meaning that has a multiplicity of 1. I have a second vertical asymptote when x equals -3. This time, no sign change, which implies multiplicity of 2. I notice that my horizontal asymptote happens at y equals 0, which means I need to solve for a. So let's put in what we know. Again, we know we have an x-intercept at 2, 0. That leads to a factor of x minus 2 with a bounce, so that has a multiplicity of 2. Our left asymptote is x minus 3. That corresponds to the factor of x plus 3. Has a multiplicity of 2, so we're going to add that power of 2. Our other vertical asymptote happens at x equals 4 with a multiplicity of 1. Again, from the number to the factor, we switch signs. And then we do not know our a value, so we put in a. We're going to use this point provided for us for x and y and solve for a. So this is 4.083. Again, we're solving for a. We're going to use that x value of -5 to solve for a. I like to do some of the simplification and multiplication before I do any multiplication across, before I grab my calculator. This is where I would want to finally pick up my calculator, multiply across. Divide that number by 49, and I get x is about -3. Again, a simple calculator will work for this. You don't need anything fancy. Make sure that when you do some of this multiplication, that I would strongly encourage you to do it in your head. I will always make sure your x value that's provided for you is a whole number, and that the only time we would probably want to use the calculator is when we're multiplying across by that decimal. At this point, I would like you guys to try this one on your own. Again, if you're watching this video on YouTube, you should be pausing the video, doing as much as you can, turning back on the video, and checking your work. I notice that I have an x-intercept at -3, 0 with a bounce. That means multiplicity of 2. I have a second x-intercept at 0, 0 with a cross. That means multiplicity of 1. Your x-intercepts belong in your numerator. I also notice I have two vertical asymptotes. When x equals -1, there is no sign change, meaning it has a multiplicity of 2. I have a second vertical asymptote when x equals 3. Again, no sign change, multiplicity of 2. As mentioned many times, if y equals 0, then we need to algebraically solve for a. And I'm going to use that point provided for x and y to solve for a. So I'm going to put in -2.05 for x, for y. And then I'm going to solve for x, putting in 7 for x. Again, making sure I've added those parentheses appropriately. I'm going to simplify this before I pick up my calculator. So at this point, I would pick up my calculator, and again, I would want to cross multiply so I can clear that fraction. And 100 times 7 is 700. Divide that 2,000 number by 700, and we get about a equals -3. I think it's 3.0032. Again, that could be just a small issue based on our point that we grabbed from Desmos. I will always do my best to have a whole x value, but your y value might be a decimal. Again, that just comes into play at the end. So our leading coefficient here is -3. Again, we want to make sure that this does fit into rule 1, where our numerator degree is less than our denominator degree. We want to check that before we do the algebra, because we might have forgotten one of those multiplicities. Now, rule 3 is the third rule in the mix. Rule 3 says that the numerator degree is greater than the denominator degree. And when that happens, there is no horizontal asymptote. The good news is that our function is created the same as the other functions. Just when we're done, we should have a higher degree in the numerator than the denominator. So I notice if I create my function, for now ignoring the fact it has an oblique asymptote, I have an x-intercept at -1, 0 with a cross. So that's going to be multiplicity of 1. I have an x-intercept at 2, 0 with a bounce. That's a multiplicity of 2. Again, x-intercepts and their behavior go in the numerator. Vertical asymptotes go in my denominator. So I have a vertical asymptote when x equals 4. Again, if I look at that behavior, it has a sign change, which means multiplicity of 1. I have a second asymptote when x equals -3. Again, sign change. As I approach from the negative side, it's going to negative infinity. As I approach from the positive side, it's going to positive infinity. That means multiplicity of 1. Now, when everything's said and done, I am complete with my function. I have a third degree function over a second degree function, and that is rule 3 because my numerator degree is greater than my denominator degree. If I wanted to find the location of that oblique asymptote, I would divide the denominator into the numerator, and the result of the division will give me the oblique. Again, it is not important the location of that oblique asymptote when creating the function. We just need to make sure and confirm that when we're done, we have a higher degree in our numerator than our denominator. I wanted to just pause for a second and remind you guys of some work that we did of simplifying rational expressions. Our steps for simplifying rational expressions are to factor, cancel, state your restrictions. Remember, we talked when we did this in December and November that anything that ever is or was in your denominator is going to lead to a restriction. As we're working today, I want you guys to see how those restrictions go into graphs of the function. So let's just start with an expression just to remind us of this. We have been doing lots of factoring, so factoring should be a little bit faster than before. Again, when we see 18 at the end, we know we're either going to use 9 and 2 or 6 and 3. I cannot have two even numbers in the same factor, so I know that the 6 has to be in the second factor because I had an even number in the first factor. Checking the signs, I want that to be a positive 9 in the middle, so I need the positive 12 minus 3. I used guess and check here. If you don't like guess and check, you can pause the video and go through the process of regrouping if you need help with that. In the denominator to factor, multiply to 48 is 6 times 8. So I have x plus 8 and x plus 6 adds to 14. Again, what I notice is that these two factors are both x plus 6, so they cancel out, and we would have 2x minus 3 over x plus 8. What we said is that anything ever is or was in the denominator leads to a restriction. So when I look at these two factors in the denominator, my two values that would have to be removed are -8 and -6. Even though this factor of x plus 6 is removed, the restrictions still apply to the whole function. Okay, so we factor, cancel, state our restrictions. Now, we're going to change that expression into an equation and see how that process, into a function, and see how that process remains the same. We are applying rule 3 here because our numerator degree is greater than our denominator degree, which fits into rule 3. We already know that rule 3 says no horizontal. Rule 3 says that then we want to check for obliques and holes. For this example, we're going to be checking for holes. A hole in the graph shows up when you have a canceled factor. So let's see how this plays out. So for this function, again, just like our last example with the rational expression, I'm going to start by factoring the numerator. What we've been talking about all along is that our numerator gives us our x-intercepts and our denominator gives us our vertical asymptotes. So because of this function, x could not equal -2, and that is the location of my vertical asymptote. After I get this function graph or factored, I notice that that x plus 2 factor cancels out and just leaves me with an x minus 2. That's a nice linear graph. But anything that ever is or was in my denominator leads to an asymptote. So when that factor gets canceled out, what it does is it removes the vertical asymptote and leaves a hole in the graph. Now the location of that hole is going to be found by putting in that x value we removed into our simplified function. So I'm just putting in that -2 into x for that linear function, and out comes -4. So that's going to give me the location of the hole. So this rational function will look like a linear function with a hole at -2, -4. Again, that point of -2 is the point that I'm removing from my domain based on the fact that it's a factor of my denominator. And my range is all real numbers, but removing that y value of the hole. What it looks like on the graph is this. So again, we see that linear function when we're creating a rational function. Again, the location of our x-intercepts are in the top. Where there should be a vertical asymptote that was removed and just leaves us with a hole in the graph. So that factor that gave us that vertical asymptote will be in my denominator. And remember, it got canceled out from something in my numerator, leaving a hole. I found the y value of the hole, again, by putting in that x coordinate into that linear function and just evaluating the function. You could also graph this with accuracy, and where that horizontal or where the vertical asymptote interacts or intersects your linear line would also be the coordinate of your y value for the hole. Now, this up, we can also work backwards. If we see a graph with holes, that tells us it's going to be a rational function. Okay. So let's build the rational function the same as we always have. Your x-intercepts go in the top. I have an x-intercept at -3, 0. And it crosses, which implies multiplicity of 1. I have a hole here where x equals -1. That should have been the location of a vertical asymptote, which means it should be the factor x plus 1 in my denominator. But remember, it canceled out to create that hole, so I have to multiply that factor in the numerator as well. I also notice I have a hole when x equals 3. That is the location of my second hole, which is the location of a second vertical asymptote. So I should have a vertical asymptote at x equals -3, but remember it got canceled out to leave a hole, so I should have that same factor in the numerator. If I was to write out my domain, I would have to remove -1 and 3 from the domain. So your domain would be -infinity to -1, -1 to 3, and then in union with 3 to infinity. So it's all real numbers for that continuous linear function, except for -1 and 3. So when we have factors that cancel out, it leaves a hole. So if we want to write the equation knowing that we have holes, we just re-add back in that factor into our numerator and denominator, so it would give us the location of a vertical asymptote. Again, if you want to, you can put in those vertical asymptote points into the linear function, which we wrote here in red, and you will get out those corresponding y values. All right, so that's it. So next time we meet, we will be taking a small test. That'll either be Monday or Tuesday, depending on what period you have class. There is no WAMAP for the weekend, just 2 small assignments on Schoolology. If you have any questions, please let me know.